Okay, this is tutorial 5 of week 6. Okay, so we'll jump right into the questions. I'll start with questions 3 to 5, followed by 1 to 2, because I think 3 to 5 are uh, more exam relevant, to use my words, but there's still value in doing question 1 and 2 because they build on the basic definitions of vector calculus. Okay, so please do 1 and 2 too. There's still value in it. I'll just go through 3 to 5 first. Okay, so question 3, find a function, okay, psi. This is the Greek letter psi. Okay, if I'm not mistaken, it's spelled like this, psi. Okay, find the function psi of x and y such that Nabla, okay, the upside down triangle, is called Nabla. Okay, Nabla of psi is this function. Okay, this vector function. Vector function. See, it's not just a normal function like we learned before. It's a vector function. See, it is some function with an I component, some function with a J component. Okay, so this is what you call a vector function. Okay, the normal functions that we encounter, let's say for example, f of x equals to x squared. This is a scalar function because there's no direction associated with it. How do I know there's direction associated with this vector function? There's the I and the J. So this dictates the direction in the I component and the J component. Okay. Whereas, for example, this is just a number. It's just a number. There's no I, there's no J. Okay. So this is a scalar function. In contrast, what we have here, Nabla of psi, is a vector function. So we want to find psi such that when you put it into this equation, this will be satisfied. Okay, so how do we do that? First, this is the first time we encountered the Nabla operator. So this thing is an operator. Operator. Okay, an operator is an item that does something to a function. Okay, for example, an operator that we are all familiar with is this, right? The derivative operator. You give it a function, let's say, for example, x squared plus x, then this will generate out another function. Okay, so if you take this derivative, it will become, okay, power bring down, power minus 1, power bring down, power minus 1. Okay, see? So this derivative operator will take the derivative of x squared plus x and then give you out another function. So that's what Nabla also does. Okay. So what is the precise definition of Nabla? Okay, Nabla is taken to be a vector. Okay, I'm gonna write in the column vector form. A vector in 3D space, it has 3 entries. 1, 2, 3. So the 3 entries in the Nabla operator is ddx. Sorry, let me be more specific. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Okay, so think of Nabla as a vector. Okay, just a normal vector. Like for example, I give you a vector 5, 3, 2. See, it has 3 entries. 1, 2, 3. Except I don't put numbers inside the entries. What I put in each entry is the derivative in the x, the derivative in the y, and the derivative in the z. Okay, so that's what Nabla is defined to be. It's just like this. Okay, and just like any vectors, if I can write 5, 3, 5, 3, 2 as a column vector, I can also write it as in the IJK format, like so. And you can also write the Nabla operator in the IJK format, like this. Okay, I, J, and then K. Okay, when you remember the Nabla operator like this, all the operations related with Nabla will become very intuitive for you. Okay, so there are 3 things that you can do with Nabla. You can do scalar multiplication. Okay, scalar multiplication. For example, Nabla of f. Okay, this is a scalar multiplication. You can do Nabla.f. Okay, so this is dot product. So this is scalar. product. Sorry, scalar multiple. Okay, scalar multiple. Then this is dot product, dot product. And then lastly, we can do cross product, cross product. Okay. Yeah, you can do all these three operations with this definition of Nabla. You just treat this just like any other vector. Okay. For example, if I tell you I want the okay, let's discuss scalar multiple first. Okay, forget about Nabla first. Suppose I give you a vector, um, 532, right? Scale. If I want to scalar multiply this, okay, so let's call this vector A. Vector A. Yeah. If I want 5 times of A, so what I will do is just say 5 and then just substitute it here. 3, 2, like that. And then what will I do? I'll just multiply the corresponding entries. 5 times this, 5 times this, 5 times this. And then I will get 25, 15, 10. Okay, so this is what you mean by scalar multiplying a vector. Same with Nabla. So suppose I have a vector function like this. Okay, let's make it xyz. Okay, this is a vector function. So let's say it's x plus y, then y squared, then z plus x, something like that. So if I want nabla of f, that means is, okay, so remember what's the definition of nabla? Nabla is just, okay, you open out a column vector, then fill it in with derivatives in each direction, x, y, and z, okay? Let's put f like this first, okay? Let's not put it in like this first. So just leave f as b. So the concept is the same. Here, when I take 5 times a, I just take this 5 multiplied by this 5 multiplied by this 3, this 5 multiplied by this 2. And then I would do the same here. So you can treat this as nabla times f. So what I do is I take this f multiply with the first entry, this f multiply with the second entry, this f multiplied by the third entry. Okay, multiplying, I'm just using it loosely here. What I'm doing is I'm not actually multiplying, I'm just inserting it into each derivative. So in the first entry, we have partial f partial x. In the second entry, we have partial f partial y. And then in the third entry, we have partial f partial z. Okay, so this is what it means to take the nabla of f, okay, like that. And then of course, you can write this in the IJK format. So it'll be like this, I plus this, j plus this, k, okay? And in fact, we have seen this before in MA2006 It's just that we simply memorize, oh, nabla of f is this. Yeah, but it comes from the fact that, okay, we define nabla to be this column vector. And then nabla of f means just take that column vector multiply with f. So you just scalar multiply f into each entry, into the x entry, into the y entry, into the z entry. Okay, so this will give you out a vector. And then same with nabla dot f. Okay, nabla dot f means, okay, so let's replace nabla with its definition, namely partial x, partial y, and partial z. Okay, so if I dot it with f, right? Okay, so what I do is, okay, now I can substitute this in. Okay, so I'll substitute f into here. Okay, and just like normal dot product, so suppose I have two vectors, 1, 2, 2, dot 2, 3, 5. Okay, the dot product of these two vectors is this times this plus this times this plus this times this. So the dot product will be 1 times 2 plus 2 times 3 plus 2 times 5. Okay? Likewise, if you do dot product with the Nabla vector, it will be this times this plus this times this plus this times this. In reality, I'm not multiplying them. I'm just taking the derivative on each of these functions. So nabla.f will be given by partial x of the first entry plus partial y of the second entry plus partial z of the third entry. It's just like in normal vectors, okay? You just take first entry times first entry plus second entry times second entry plus third entry times third entry, just like normal dot product. And lastly, cross product. Okay, so suppose I have cross product. Okay, remember you treat this as a vector too. So suppose I have 1, 1, 1 cross 2, 3, 1, something like that. Okay, so to find the cross product of these two vectors, remember what you need to do is you must find the determinant of this. So I, j, k, then the first row contains the entries of the first column vector, 1, 1, 1. The next row contains the entries of the second vector, so 2, 3, 1, like that. And then you will find the determinant of this thing, okay, using the crisscross method that I covered last week. So go ahead and check the tutorial if you need to. Okay. Likewise, okay, so I'll just put this down here for comparison. Okay, so let's substitute each definitions in. So Nabla, remember, we defined it to be partial in the x, partial in the y, partial in the z. Okay, remember we treat Nabla as a vector. Then cross, so remember we have already defined f to be, okay, this is the x component, this is the y component, and then this is the z component. So what I need to do is, just like normal cross product between vectors like this, so what I need to do is, okay, to find the Nabla cross f, you find the determinant of I, j, k. So the first row here contains entries of the first vector. Here our first vector is this one, right? So the entries of the Nabla vector are partial x, partial y, partial z. Okay, then the entries of the f function will be this. Okay, so x plus y squared, z plus x. So this is what you mean by Nabla cross a function. Okay, Nabla cross a vector function. So basically, what you need to do at the end of the day is remember that Nabla is defined to be a column vector with these entries. Okay, partial derivatives in each direction, in the x, y, and z direction. Then after that, you just treat Nabla like a normal vector. So you can do scalar multiplication, you can do dot product, you can do cross product. Okay, simple as that. Okay, so anyways, let's go back to this question that we need to focus on. So find find psi such that Nabla of psi will satisfy this vector equation. Okay, so uh, okay, so let's focus on the left-hand side first. In the left-hand side, we have Nabla of psi. Okay, so let us replace Nabla with its definition. Okay, so remember, Nabla is just a vector containing partial derivatives as its entries. Okay, partial derivatives in the x, y, and z direction. Okay, and then just leave psi to be. Okay, so remember, we can treat this as normal scalar multiplication, meaning this time this, then the next entry will be this times this, and then the last entry will be this times this. So this will simply be like normal expansion, like this, and like this. Okay, sometimes it's very it's too much of a handful to write partial derivatives, right? You see, I always take so much time to write partial derivatives, right? Writing this thing takes such a long time, and you have to do this multiple times. So people do an abbreviation. Okay, abbreviation means the short form or the shorthand. Okay? Abbreviation. Okay, just to make it short, they denote partial derivative with respect to x like this. Psi with a subscript x. Okay. Likewise, they denote partial derivative with y with respect to like this. Okay, with respect to y, sorry, psi with respect to y like this. So psi with a subscript y. And then similarly, partial derivative with respect to z is psi with a subscript z. But if you forget this, you can just stick to using these partial derivatives. But I'm telling you, it's gonna be a lot of things to write. Okay, don't worry. Anyways, just FYI. Okay, so I'm gonna put here FYI. We abbreviate it. Okay, just abbreviation. Abbreviate. Abbreviate means make it short. As psi of x, psi of y, and psi of z. Okay, so let's go back to here. Notice that we have a I component, j component, but no k component. Okay, so the k component here is 0k. Okay, so we do not have to care about this, the partial derivative with respect to z. Okay, there's no such entry here. Okay, so we only need to focus on the first two entries. So what does it say? It says that nabla of psi is equal to this right hand side. We have already found that nabla of psi is this. Okay, so let me just write this down. Okay, we have found nabla of psi is equal to this. And they also told us nabla of psi is this right hand side. So what do? We need to um, equate them, right? So if two vectors are said to be equal, right? If two vectors are said to be equal, that means the x entry will be equal. So this x entry will be equal to this, and then the y entries will be the same. So this y entry will be equal to this. Okay, so that's what it means for two vectors to be equal. Okay, so let me write that down. Okay, so let's deal with the x entry first. So we know that partial derivative of psi with respect to x will be equals to this red box. Okay, I component with I component. So let's write that down. Partial derivative with respect to x is equal to, okay, so we need to copy this down. Okay, I'm going to copy it down. So it says in the question, this is oh, it's really that long. Let me check. Yeah, it's really that long. Okay, so now our objective is to make what the psi the subject, right? Because they said find the function psi. So we need to make psi the subject, meaning say we need to make psi alone. So you see, psi is enclosed in this derivative operator. We need to take it out of the derivative. So what's the opposite of differentiation? It'll be integration. But this is a partial derivative, right? So take note that we're not just doing ordinary integration, we are doing partial integration. So I'll show you what I mean. So let's do integration on both sides. Partial integrate with respect to x on both sides. So this integration will cancel with this derivative operation, leaving you psi only. And then on the right hand side, we need to partially integrate this expression with respect to x. Partial integration means, okay, so let's say here we have a partial integration with respect to x, right? So to partially integrate with respect to x means you treat all other variables as constants. So x is the thing that we need to, is the variable that we need to integrate with respect with. So what are the other variables that show up? For example, y. Y is another variable that shows up, right? But we shall treat y as a constant. We just treat it like any number. okay, we will treat y just as much as it is just like 2, okay, for example. So partial derivative with respect to partial integration with respect to x means I just treat y like a constant. So let's go ahead and do that. So for the first term here, we need to integrate sine 2x, okay? So this is just a constant, copy it down, okay? So we need to integrate this. So integration of sine will be cos, negative cos, right? Negative cos 2xy. Then don't forget to divide by the derivative of the inside. So differentiate this partially with respect to x, okay? The partial derivative of this with respect to x will be 2y. Remember, we treat y as a constant, okay? Next, we will integrate this term. So 4y is just a constant, so copy it down. Integrate this with respect to x, okay? So integration of cos is just sine. And don't forget, divide by the differentiation of the inside with respect to x. So y is a constant, so it will be divided by 2y. Integrate this, so it will just be power plus 1 divided by new power. Power plus 1 divided by the new power minus, okay, integration of a constant, just insert x. Okay, so here's the tricky bit. Normally, when we do an integration, right, we need to add the arbitrary constant c. But here, we shall add the arbitrary constant as c, hold on, c as a function of y. Okay, let me label this subscript 1 because later we have another arbitrary constant. Okay, so what do I mean? Let's say I give you integration of x squared dx. So everybody knows power plus 1 divided by a new power. Then you always add the arbitrary constant, right? But this is just a number. A number. In this case, this is not a number. This is a function. Okay? And to be specific, it is a function with respect to y. Remember, we have two variables, x and y. But this is a function. This is a function of y, right? Because remember, we are partially integrating with respect to x. When we do partial integration, we treat y as constants. Therefore, this function must be a function of this constant, arbitrary constant, must be a function of y, because y is seen as a constant. Okay, so therefore your arbitrary constant is a function of y. Okay, so that's why. Okay, long story short, right? Long story short, if you didn't quite catch that, long story short is if I partially integrate with respect to x, my answer will have a arbitrary constant with respect to y. In the opposite case, if I partially integrate with respect to y, my answer must have an arbitrary constant that is a function of x. So you see, partial integration with respect to x has an arbitrary constant as a function of y. Partial integration with respect to y has an arbitrary constant which is a function of x. So you see, it's reversed. Okay, anyways, we'll simplify this. Minus and minus can cancel. 2y and 2y can cancel. 2y and 4y, so this will become 2. Okay, so this will clean up to become cosine 2xy plus 2 sine 2xy. Okay, 4 and 4 can cancel. Okay, so this is our first side. We still need to consider the j component. Remember, just now we got this from considering by equating the I components, right? We equated this with this. Now we need to equate this with this. So we are equating the j terms. The j term with the j term. Okay, the j component with the j component. So let us go ahead and do that. In the j component, from Nabla, we have, from Nabla of psi, we have a partial derivative with respect to y is equal to, and then from the function that they gave us, it'll be minus 2x sine 2xy plus 4x cos 2xy plus 5y 4 minus 12y. Okay, so let me check if I copy that correctly. Okay, so as far as I check, it looks correct. So again, we need to make psi the subject, right? So to take out psi from the derivative, we need to integrate with respect to y, partially integrate. So integrate will cancel with differentiate, leaving psi. Integrating this side, okay? So remember, now we are partially integrating with respect to y. We treat x as a constant. So this, copy it down because it's a constant. Then integrating this, so integration of sine is negative cos. Then don't forget, divide by the derivative of the inside with respect to y. So this will become 2x because x is seen as a constant. Plus, okay, 4x is a constant, copy it down. Integration of cos is sine divided by the differentiation of the inside. Okay, so this one, power plus 1 divided by the new power. Then this one also, power plus 1 divided by the new power. And don't forget, when you end, you need to put your arbitrary constant. Okay, this time it is a function of x. So it's the opposite thing to which you are integrating with respect with. Okay, so now we can simplify. 2x and 2x can cancel. Minus and minus can cancel, leaving you cos 2xy. 2x and 4x can cancel. This leaves you 2 plus 2 sine 2xy. 5 and 5 can cancel, leaving you y5, y to the power 5. This and this can cancel, leaving you negative 6y squared, plus c2, which is seen to be a function of x. So this is the second psi that we obtained from considering the j component. So now what do we need to do? We need to know that, okay, this psi that we obtained is equal to this psi we obtained. Okay, the psi that we obtained from the I components is the same as the psi that we are obtaining from the j components. But we do not know the arbitrary functions yet. See, we don't know what is this, and we also do not know what is this. So we need to find it out. How do we find it out? We compare the results that we obtain. Okay, so first thing first, I want you to copy the results that you obtain from each component. Okay, so let us copy this first. Then also this one, should copy it. Okay, so here is a plus c2x. Okay, so now I need to compare. So let's compare results to find C1 and C2. Okay, so let's find matching terms. Okay, so I want you to look at the first equation of psi and the second equation of psi and see what terms match. Notice that this and this match. Okay, so good. This and this match. Okay, now the difference between these two, right, is this. Everything left behind here is the true difference between the psi at the top and the psi at the bottom. Okay, and take a look at this. C2 is said to be a function of x. Do you notice that this is also a function of x? You see, everything in here is just in terms of x. Likewise, C1 is said to be a function of y. Do you notice that these terms are a function of y? You see, it's y to the power of 5 minus 6y squared. So C1 is actually y to the power of 5 minus 6y squared. And then C2 is actually this x to the 4 minus 2x. Okay, so from this comparison, we can tell that C1 is equal to y5 minus 6y squared, and C2 is equal to x4 minus 2x. Okay, so it doesn't matter what you take. So let's okay. So this comes from the second version of psi, okay? The second version of psi that we got. And then what we want to do is we want to replace C2 with what we found. Remember, we found that C2 is this. So we shall make this replacement. So replace C2 with x to the power of 4 minus 2x. Okay? So let's go ahead and do that straight away. So sub C2 equals to x4 minus 2x into sine. Okay, so what you do is you just replace this with x to the 4 minus 2x. Okay? And well, you can stop here, but I need you to do this. You need to plus k here. Okay? You need to plus k. This is just like your arbitrary constant that you do in integration. So after you found psi, right? Don't think that you can stop your journey here. You need to add this k. This is your arbitrary constant. Okay? This is your arbitrary constant. Because sometimes, right, you need to find this value of k. Okay? Sometimes you need to find this value of k. I don't know why in the answer they just left out this k, but in general, you must put this k. So you find psi first, and then after you found psi, you still need to plug in this k. Okay, so I will show you a question which needs this k later. Okay, so anyways, this question is done. Now we move on to question 4. Okay, so question 4 states that we have a function given that all points on xyz is such that nabla of f is 0. So take note that this is not just 0 as a number. This is a 0 vector. You see this underlying line? I can also write it like this. This is a 0 vector. Meaning to say it's written like this. Okay, a vector with 0 in each of its entries. So this is what you call a 0 vector. It's not the same as 0 as you know in the number. So nabla of f is equal to the 0 vector. Give a geometrical interpretation of those points. Okay, so what you need to do is you need to find the nabla of f. So nabla of f, remember, so replace nabla with its definition, namely partial derivatives in each direction. So this is the definition of nabla. And then remember f, so what you can do is you treat this as a scalar multiplication. So meaning you just expand it, just like how you would expand a normal column vector, like this, and like this. So it will become, so you will now know that nabla of f is like that. Okay? So they are saying that this nabla of f is equal to the 0 vector, meaning that this will be equal to 0, 0, 0. Okay, so now you know that partial f partial x is 0, partial f partial y is 0, partial f partial z is also 0. Okay, so this is what they are trying to tell us. So what we need to do is we need to first obtain these partial derivative expressions. Okay, we need to first obtain these partial derivative expressions. Okay, so let's find df dx first, which is ddx of this entire expression. Oh my goodness. X squared plus y squared plus, what is it? 3z squared. 3z squared plus xy plus 3xz plus 3yz plus x plus y plus 2z plus 10. Oh dear, that's 2z plus 10. Okay, never mind, because this is partial derivatives, right? So if I'm partially differentiating with respect to x, I treat the other variables as constants. Here, the other variables are y and z. So y and z are constants. Remember that partial derivative of a constant, okay, derivatives of a constant is just 0. Okay, for example, derivative of derivative of 5 with respect to x is 0, right? Then ddx of 2x plus 1 is equal to 2. how do I get this 2? This 2 comes from here, whereas differentiation of 1 is just 0. Okay, it becomes nothing. Okay, so remember, differentiation of a constant is 0. Okay, so let's do that. So differentiate this, power bring down power minus 1. Then you see, y is a constant, z is a constant, so this will just become 0. Then we treat y as a constant, right? So partial derivative of x with respect to y, it will just be y. Okay? So it's just power bring down power minus 1. So power minus 1 means x to the 0, which becomes 1. Then we're just left with the y. Okay, so this becomes y plus, so z is seen as a constant, so 3xz will just become 3z. Then, see, y and z are constant. Remember, derivative of constant is just 0. Then, derivative of x is just 1. Derivative of y is just 0 because it's a constant also. Derivative of 2z is just 0 because it's a constant also. I'm not going to write this. Then derivative with respect to derivative of 10 is a constant, so it's also 0. Okay, so the last 3 terms are all 0 because derivative of a constant is 0, 0, 0, 0. Like that. So we have our first partial derivative. Okay, we need to do the same thing with derivative with respect to y. So let me copy this down. Clean this up. Okay, I'm gonna do it a bit quicker now because we should be familiar with partial derivatives at this point. So now we need to do partial derivative with respect to y. So you see, x is a constant, z is a constant. What else? Y alone is a constant, 2z alone is a constant, 10 is a constant. Sorry, y, remember we are partially differentiating with respect to y. So z is a constant. Okay, x is a constant, 2z is a constant, 10 is a constant. Okay, we're now partially differentiating with respect to y. So y squared will be power bring down power minus 1. Xy will be just y. Sorry, we are partially differentiating with respect to y. So it becomes just x. Okay, 2z. Alright, xz is also just a constant. Then this will become 3z. Okay, just remove the y. And then the derivative of y is just 1. Yeah, let me check my solution. 2y plus x plus 3z plus 1. Yep, I'm correct. Okay, and lastly, we need the z derivative. Okay, so let's see if we have any constants to throw away first. So remember, we are differentiating with respect to z. That means x and y are our constants. 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 And also 10 is a constant. So now we need to differentiate this with respect to z. So power bring down power minus 1 plus, so this one just remove the z. We're left with 3x plus, this will become 3y, and this will become 2. Okay, yes. So now we have our 3 derivatives in the z direction, in the y direction, and in the x direction. And remember what we said? We said each of these derivatives is equal to 0. See, this is equal to 0, this is equal to 0, this is equal to 0. So let us take these 3 equations and then equate them to 0. Okay, so let me just write them down. So this is the x derivative. So remember, the x derivative is equal to 0. The y derivative is equal to 0. The z derivative is equal to 0. Okay, so now let us rearrange this equation such that it is in the form ax plus by plus cz is equal to d. Okay, meaning I need to move all these constants to the other side. So move them to the other side. I will get minus 1, minus 1, minus 2. Once that is done, I can finally write my augmented matrix. So we are now going to solve for x, y, and z, right? This is a system of 3 equations and 3 unknowns. We need to do Gaussian elimination. First, write them in the augmented matrix form. So these coefficients, you will copy them down in a 3 by 3 augmented matrix. So remember that, okay, let me write this down first before I talk. Okay, so remember that this column is the coefficients of x. This column is the coefficients of y. This column is the coefficients of z. So you see, they're not ordered in x, y, z. See, this is y, z, x, then this is z, x, y. So remember to put the coefficients in the correct position. Okay, so each column is the coefficients of each direction. In the x direction, in the y direction, in the z direction. So coefficients of x, coefficients of y, coefficients of z, followed by the constants. So now we can do Gauss elimination. So what is our objective in Gauss elimination? We need to make this in upper triangular form. We need to say that we have an upper triangle here with all these, the lower triangle being 0. Okay, so all these must be eliminated to become 0. Okay, and then here's a tip. If you can, right, make these diagonal entries equal to 1. You don't have to, but it would be nice if you can. Okay, but the most important thing that is mandatory for Gauss elimination is that the lower triangle is all 0, 0, 0. Okay, so let's go ahead and try and do that. Okay, so what am I going to do? The first thing that I will do, right, is to do a row swap. Row swap between 1 and 2. Okay, so what will this become? If I do a row swap, okay, so row 2 will come up here. Row 1 will take row 2's place, like that. The reason why I do this, right, is so that this will become 1. Remember, I said if you can, right, make these diagonal entries all 1, if you can. Okay, so now we are going to use this 1 to kill the 2 and kill the 3. When I say kill, I mean to eliminate. Eliminate, okay? So row 2 will transform to become row 2 minus 2 row 1. Row 3 will become row 3 minus 3 row 1. Okay, so I will explain why I do these set of row operations. So first, let us compute 2R1. Okay, let us calculate what is 2R1. 2R1 means I take the entries in row 1, multiply them by 2. So 1 times 2 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times minus 1 is minus 2. Okay, you see, when I take row 2 minus 2 of row 1, right, I will take this entry minus this entry. You see, 2 minus 2 will become 0. That is how you kill this entry here. That's how you knock out that 2 in the second row. Okay, so that's why I take row 2 minus 2 row 1. Likewise, let us compute 3R1. So let's calculate out what's 3R1. This means that I take the entries of row 1 and multiply them by 3. So 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, negative 1 times 3 is minus 3. Okay, so now I will perform these row operations. Let us do row 2 minus 2 R1. This minus this is 0. 1 minus 4 is minus 3. 3 minus 6 is minus 3. Minus 1 minus minus 2 is minus 1 plus 2. So 2 minus 1 is 1. Okay, yes, I'm correct. I need to check because I can make careless mistakes. Okay, so now let's do the second row operation. Row 3 minus 3 row 1. So 3 minus 3 is 0. 3 minus 6 is minus 3. 6 minus 9 is minus 3. Then minus 2 minus minus 3. Okay, minus 2 minus minus 3 is positive 1. Okay, finally, we will try to eliminate this, right? Because remember, we want to make this lower triangular matrix all zeros. Meaning to say we need to eliminate this. Okay, so we're going to use this to kill him. And they just so happen to be the same. So we can directly take row 3 and replace it with row 3 minus row 2. You see, this row minus its exact same self. Means that row 3 will become all zeros. Okay, so row 3 will become all zeros. Copy that and then paste. 0, 0, 0. Okay, once we have it in upper triangular form, yes, this is upper triangular form. See, all the entries below this upper triangle is 0. See, all here are 0. So once you have it in upper triangular form, we can finally solve it from the bottom row to the top row. Okay, let us start from the bottom row. Okay, consider what the bottom row says. Okay, we can forget about the first entry and the second entry. Okay, focus on the z entry and the other side. So this is saying 0z is equal to 0. Okay, and then, like I said last class, right, the logic behind this is in last class. Any value of z can satisfy this equation, right? Try plug in z equals to 1. See, 0 times 1 will become 0. Yes. Try z equals to 2. 0 times 2 is equal to 0. Try z equals to negative 1. 0 times negative 1 is still 0. Try z equals to all the way until 100. See, 0 times 100 is still 0. So any value of z can satisfy this, right? So when you deal with 0 equals to 0, this kind of case, 0 equals to 0, then you use the free parameter. So let z be equals to t. So t is what you call the free parameters. Now we move on to row 2 and try to solve for y. So row 2, right? You see, these are the coefficients, and then this is a constant. Row 2 is saying minus 3y minus 3z, okay, is equal to positive 1. Okay, so where did I get this minus 3 minus 3? I got it from here. Minus 3 minus 3. Okay? And then remember, from row 3, we already found that uh, z is equal to t. So we shall substitute it into here. Okay, so now you replace z with t. So minus 3y minus 3t is equal to 1. And now make y the subject. So minus 3y is equal to, then you divide both sides by minus 3. Okay, divide this by minus 3, divide this by minus 3, divide this by minus 3. Okay, so now this is your solution for y. Then you will use this and then sub it into row 1. So now row 1 will help you solve for x. So you see, these are the coefficients. This is the constant. So what the first row is telling me is positive 1x plus 2y plus 3z is equal to minus 1. See? The 1, 2, 3 goes to here. 1, 2, 3. So that's how I write the first equation. Okay? So now, using the results that we got earlier, namely y equals to this, and then z is equal to t, we shall substitute it into here and here. So and then now we shall make x the subject. So this is that minus 2t plus 3t, then minus 1. Okay, I'm going to go skip forward and make x the subject. So x will become minus 1 over 3 minus t. Okay, so now see, we finally have the solution for x, the solution for y, and then the solution for z. So let us write them down in this form. So x, y, z, right, is equal to Okay, so you can stop here, right? But then they also ask, give an interpretation for the solution. Okay, give an interpretation, a geometrical interpretation of these points. Okay, so I want you to write it in this further form. So let's see. Let me show you what I mean. So you see, in front of here, right? In front of the t's, there's always a number. This is a fraction. This is a fraction, and then in front of here, there's also a number, and that number is just zero. Zero plus that. Okay. So what I want you to do is, you will segment these numbers. This, you write it as one column, and then the t's, you write it in another column vector. Okay, you write them as two separate. You split them up. You write them in two separate column vectors. So you see, this is what I mean. So minus 1 over 3, minus 1 over 3, and 0, you write them in one column vector. And then the second column vector, you write the t's, minus t, minus t, t. And then the next thing I want you to do is factorize out t. Factor out t. Okay? When you do this, you shall get... Okay, so I factor this out, right? T will come outside here. Then we have minus 1, and 1. Does this look familiar to you? Yes. In fact, right, this is the general form of a straight line equation. Okay, straight line in parametric form. Remember that for any straight line, okay, any straight line has the parametric form like this. So x naught, y naught, z naught plus t, and then a, b, c, where x naught, y naught, z naught, right, is the coordinates of a known point on the line. Is a point on the line. Point on the straight line. Okay, straight line. And then ABC is a vector parallel to the line. Okay, it's a vector that's parallel to line. So when you draw this equation out, it will give you a line. And then there is this point on the line. So there is a point minus 1 over 3, minus 1 over 3, 0 on the line. And then this line is also parallel to this vector, to this vector. Okay, it is parallel to the vector. Okay, let me write this in column vector form. Minus 1, and 1. Okay? Okay, so the geometric interpretation is, it is a straight line passing through the point minus 1 over 3, minus 1 over 3, 0, parallel to the vector. Okay, you can write this as a column vector form, minus 1, minus 1, 1. Or you can write this in the IJK format. So in the IJK format, right, it'll be minus I, minus j, plus k. Yeah. Okay, so this is the geometric interpretation. Moving on to question 5. Okay, by the way, right? By the way, I covered this formula, this equation of a straight line in the last class. So if you don't know it or this doesn't look familiar to you, look at it in the last class. Okay. We want to find the function phi. So this is a Greek letter phi, F-H-I, which is different from psi, okay? Psi is like this. Psi looks like a fork. This psi. And this is phi. So we want to find the function phi such that nabla of phi is given by this vector. And then we are also given an additional condition. Okay, this condition states that at the coordinates 1, 3, right? At the coordinates 1, 3, phi has a value of 5. So we need to satisfy both of these. Okay, this and this. Okay, so let's go ahead and do that. So let's consider the left-hand side first, nabla of phi. So what is nabla of phi? Remember, you just replace nabla with its definition. So the definition of nabla is a column vector containing partial derivatives in each direction. Okay, then you put 5. So you see, you treat this as a scalar multiplication. Take this time this, this time this, this time this. In actuality, you're not taking multiplication, you're actually just chucking it into the each entry. Okay, now that we found Nabla of 5, they told us that Nabla of 5 is equal to this. So what this means is now we need to equate each components. So remember, this is the I component, J component, K component. There's no K component in this question, right? So we don't need to care about this. So this I component is equal to this I component. This J component will be equal to this J component. So let us first consider the I components. So the I component states that d phi dx will be equal to this I component, 3x squared. So that's actually squared, there's a typo, plus 4y. Okay? Remember, we want to find phi. Okay? Our question says find phi. So we need to make phi the subject. Let us take the partial integration of both sides to get rid of the derivative. Partial integrate with respect to x. Integration cancels with differentiation, leaving behind phi. And then here we need to partially integrate with respect to x, meaning y is a constant. So this one, power plus 1 divided by new power. This one, y is a constant. So just plug in, attach x to behind. Yeah. Plus, don't forget, you need your arbitrary constant. But since you are partially integrating with respect to x, your arbitrary function will be a function of y. Okay? Simplify, leaving behind. Okay, so this is your first phi. Now you need to consider the j components. So please equate the j components. So the j components has, okay, partial phi partial y is equal to this j component, the highlighted green. Okay, so now we need to partially integrate with respect to y. Okay, integration cancels with differentiation, leaving behind phi. Partially integrate with respect to y means x is a constant, so power plus 1 divided by new power. Then this one just treat it as a constant, so just attach y. This one also treat it as a constant, so attach y. And don't forget, you're partially integrating with respect to y, means your arbitrary function will be a function of x plus c2 x. Okay, now simplify. 2 and 4 can cancel to become 2. You are left behind with 2y squared plus 4xy plus 3y plus c2x. Okay, now we need to compare to find c1 and c2. Remember, the arbitrary functions are unknown, so we need to find them. c2. Okay, so take the two results that you obtained, copy, paste. Okay, and this one also. And then play a game of matching. So see what terms match in the top side and the bottom side. So you see, this matches with this. Okay, so we can ignore that. Okay, and the rest are different. Okay, so the rest of the terms are different. Okay, let's look at this. We want to find c1. c1 is a function of y. So wherever you see the terms that have y, that will be your c1. So you see, 2y squared plus 3y are all a function of y. Okay. In contrast, x cubed will be this, right? See, x cubed is a function of x. Therefore, c2 will become x cubed because c2 is a function of x. Okay, so from this comparison, you can say c1 is equal to 2y squared plus 3y, and c2 is x cubed. Okay, so we can just take sub c2 into psi. Okay, so Meaning to say, I'm going to take this, I'm going to replace it into here. Okay. Alternatively, right, you can just take this and replace it into here. They both give you the same thing. Okay. They both give you the same thing. Okay. So, anyways, I'm going to paste, and then the C2 that I obtained, so this C2, I'll replace it here. So let me just replace it straight away. We have x cubed. And don't forget, after you do this replacement, right, remember, put plus k. And now, this is the question where this k will be useful. Why? Because don't forget, we are not done yet. We've, up until this point, right, we have only satisfied the first condition. The first condition states that Nabla of 5 is equal to this vector function, but we have not satisfied this one yet. Okay, so now we need to satisfy phi at 1, 3 is equal to 5. So this states that when x is equal to 1 and y is equal to 3, then phi will be equal to 5. So this is what this equation is telling us. Okay? This is what this equation is telling us. So let us go ahead and do those substitutions. So you see, replace phi with 5. Okay. Then wherever I see y, I replace it with 3. So 2, 3 square plus 4. And then wherever I see x, I replace it with 1. 1, 3, 3, 3, 1 cube plus k. You see, now the only unknown in this equation, right, is just k. So just solve for k, and I tell you, k will become minus 35. Okay? Yeah. Once you found this k, right, remember to substitute it back into here. Okay? So let us go ahead, copy this. Okay, now I need to put this k into here. Okay, if I do that, so let me just write down the instructions here. Sub k equals to minus 35 into 5. So this will become, sorry, minus 35. Ta-da! And then this is your solution. This is your solution. So phi equals to this function. You see? So don't forget, after you found phi, right? Don't leave this blank. You must put this arbitrary constant plus k, so that when they give you a, this is what you call a boundary condition. Okay, actually it's just a condition. It doesn't have to be a boundary condition. Yeah, so that when they give you this condition, right, then you can solve for that arbitrary constant k. So please put the k after you found your function. Okay, yeah. So yeah, those are the tough questions of this tutorial. Now let's go to the easier ones. Okay, the easier one, it doesn't mean that they are useless, they are useful, okay, in building our definitions. So hold on first. I need to go ahead and do something. Okay, I'll be back in a moment. Okay, question 1. For the vector function this, okay, notice that this is a vector function. How do we know? Because there's I, j, k. It's not just a normal scalar function that we are familiar with. So this is a vector function. We want to find each of these expressions. So let's go ahead and start. So g dot g, meaning to say we need to dot product itself. So let's go right in column vector form because I like to do dot product in column vector. It's very easy to see that way. So fill in each entry with the I entry, the j entry, and then the k entry. Then do the same thing because it's g dot itself. Okay, so remember dot product means you multiply the corresponding entries and add them all together. This time this, plus this time this, plus this time this. Okay, so you go ahead and do that. So you see, it's multiplying by itself, right? Means this thing squared plus the y entry squared plus the z entry squared. Okay. Next thing you do is you expand it. So okay. So pay attention to the first two terms. They have a common factor of 9, right? So let us go ahead and factorize 9. Okay. You can write this as cos squared 2t plus sine squared 2t, but I prefer to write it the other way around, and you'll see why later. So I'm gonna just flip it around. And the reason why I do that is because this looks like a very familiar form. Okay, this is actually the Pythagoras identity. Okay, so remember the identity: sine squared a plus cos squared a is equal to 1. That means I can replace this term with 1. Okay, I can neatly replace this term with 1. Okay, so replace this term with not 1. You have this, and then you simplify this, it'll become 10. Okay, so that's the answer to the very first question, 10. Okay, notice that dot products, right? Dot products of two vectors is a scalar. See, this is a scalar, right? It's not a vector. It's not a vector, right? There's no I, j, k, and it's not written in a column vector form. So the result of dot product is a scalar. So it's just a number, an ordinary number. Then conversely, okay, in the opposite case, the result of cross product is a vector, right? If I take two vectors, A and B, right? Remember the cross product, A cross B, will be a vector that's perpendicular to both of them. So this is A cross B. Notice that it is perpendicular to A, and at the same time, it is perpendicular to B. So that is cross product. So long story short, right? The result of dot product is a scalar. The result of a cross product is a vector. Okay, it's always the case. Okay, move on to question B. So now we want dg dt dot itself. Okay, that we need to find what is dg dt. So what is dg dt? This means that we need to take a time derivative of the function g that they gave us. So let us go ahead and do that. Now, how do I take the time derivative of this? I just differentiate the first entry, differentiate the second entry, differentiate the third entry. That's it. Okay, that's it. So let's differentiate this with respect to t. So negative 3 is just a constant. Differentiation of cos is minus sine. Then don't forget, multiply by the differentiation of the inside because of chain rule. Next, differentiation of sine is cos, and then don't forget to multiply by the differentiation of the inside, also because of chain rule. And then derivative of a constant, okay, 1 is just a constant, it's just 0, so just 0. Okay, so now you simplify this to get your dg dt. So minus 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 is plus, 2 times 3 is 6. 3 times 2 is 6. Okay, finally, once we obtain dg dt, we can dot product itself, which is what the question wants, right? So the question wants this dot itself, meaning to say you copy that thing, the result that we got, you dot it with itself. Okay, so remember dot product means multiply the corresponding entries, add them all up. This time this, plus this time this, plus this time this. So this will become, okay, so since it's multiplying exactly by itself, we can just write it as squared plus this thing squared, and then it's just 0 squared, so I'm not gonna write that. Okay, then we can expand this. So 36 sine squared 2t plus 36 cos squared 2t. And then, see, both of them have a common factor of 36. Factorize that out. And then notice, this is the identity that we saw earlier, right? Remember that sine squared a plus cos squared a is equal to 1. Meaning say, we can just replace this whole term with 1. Right? Yeah, 1. So 36 times 1 is just 36. So that's your second answer. Let's go to the question C. Question C says G dot dg dt. So you take your G that you got, write it in column vector form. And then you take your dg dt that you derived. And then now you dot product. So dot product means multiply the corresponding entries, add them all together. This time this, plus this time this, plus this time this. Okay. So if you multiply these two together, minus 3 times 6 is minus 18. Cos 2t sine 2t. And then 3 times 6 is plus 18 sine 2t cos 2t. And then 1 times 0 is 0, so I'm not going to write that. So you see, actually these two are exactly the same, except they have opposite sign, right? One is positive, and then the other one is negative. So they will just cancel, right? Something minus itself is just 0. So this becomes 0. Okay? I want you to pay attention to this. You see, we take these two vectors, this is a vector, this is a vector. We dot product them, and the result is 0. So pay attention to that. We know that g dot dg dt is equal to 0. And this is a useful result when we do question D. So let's check what's question D. Question D states, we want to find the magnitude of g cross dg dt. Okay, so let's go ahead and find it. Magnitude of g cross dg dt. Okay, so one painful way, right, will be to find g cross dg dt. But that's difficult. Why? Because you need to find this the determinant of I, J, K, and then the G entries, the dg dt entries, and then you need to do Sarus's rule, which is the criss, 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 cross, cross, cross. But that's very difficult, right? So here's a hack. And then the question told us there's a hack. So let's read the question. Hint. The answer for part D can be deduced from A, B, and C. What does your answer in C tell you? So let's look at our answer in C. Remember that we found in C, the dot product of these two vectors is equal to 0. This vector, dot product with this vector is equal to 0. Do you remember last class? I said an important theorem. Okay, the theorem states that dot product of two perpendicular vectors is equal to 0. This is an important rule. So we see, we know that g dot dg dt is equal to 0. This tells us that g is perpendicular to dg dt. Okay, remember that the dot product of any two perpendicular vectors is 0. And let me quickly go through y again. So suppose I have vectors a and vectors b who are separated by an angle of 90 degrees. This is a, this is b. They're separated by an angle of 90 degrees. A dot b, there's another formula for dot product, and it is magnitude of A, magnitude of B, cosine theta, where theta is the angle of separation. Since the angle of separation is 90 because they are perpendicular, you can evaluate this. Cos 90, right, is equal to 0. Yeah. So see, you see? So when theta is equal to 90, meaning to say when the two vectors are perpendicular, A dot B is 0. Okay? So here's the conclusion. If A is perpendicular to B, then A dot B is equal to 0. You must remember this. For two perpendicular vectors, the dot product is 0. And then from question C, we found that the vector G and the vector dg dt, the dot product is 0. So this is implying to us that G is perpendicular to dg dt. Meaning to say, the vector G and the vector dg dt have an angle of separation of 90 degrees. Okay, so let's keep note of that. Now we want to find the magnitude of the cross product. I'm sure you've seen this rule before. I mean, this formula before. I'm sure you've seen this formula for cross product before. So the cross product, okay, the magnitude of the cross product of two vectors is given by magnitude of A, magnitude of B. Instead of sine, right, it'll be, sorry, instead of cos, right, it'll be sine theta. Okay, so for two vectors A and B, the cross product magnitude is given by this formula. So likewise, we shall do the same thing. So we want G cross dg dt. Applying this formula, we will get magnitude of G times magnitude of T sine theta, where theta is the angle of separation. Question C tells us, okay, C tells us that G is perpendicular to dg dt, which means that the angle of separation is 90 degrees. Okay, and how do I know? This is because, okay, this triple dot means because this dot this, okay, the dot product is 0. Remember, if dot product of two vectors is 0, that means these two angles are 90 degrees apart. Okay, dot product of two perpendicular vectors is 0. Yeah. So once you know that g dot dg dt is 0, that means the angle of separation is 90 degrees. So you can substitute this. You can substitute this theta equals 90 into here. Let's go ahead and do that. So sub this, it become 90. Sine of 90, right, is equal to 1. Very nice. So now we need to find magnitude of G, magnitude of dg dt. It's very, very simple, very simple. These two are vectors, right? These two are vectors. For a vector which has the, okay, if I give you a column vector which has the entries A, B, C, to find the magnitude of this vector, you just take the square root of A squared plus B squared plus C squared. Yeah, which is the Pythagoras theorem. Yeah, Pythagoras theorem. So that's what you do for magnitude of G and magnitude of dg dt. So let's this will become magnitude of multiplied by the magnitude of dg dt. Okay, so let's calculate this. So take square root of the first entry plus square root of the second entry plus square root of the third entry. Okay, and then don't forget the magnitude of dg dt. So square root of the first entry plus square root of the second entry plus square root of the third entry. Okay, so let us go ahead and simplify this. So you see, notice inside, it'll become what? Here it'll become 3 cos squared 2t plus 9 sine squared 2t plus 1. Okay, I'll evaluate the second square root later. You see, this can become 9 sine squared 2t plus cos squared 2t, which I already told you this is just 1. Okay, so 9 times 1 is 9. Then don't forget to plus 1, it'll become 10. So the first square root becomes square root of 10. Okay, let's look at the other side. Now the other square root, this is, so 0 squared is gone. 36 sine squared 2t plus 36 cos squared 2t. We can factorize 36 from here, right? So you see, I can factorize this as 36 sine squared 2t plus cos squared 2t. Again, this is just 1, right? This is just 1. So this other side, right, will just simplify to square root of 36. Square root of 36 is just 6. So this will become 6 root 10. That's the answer. Okay, so that's question 1D. Now we're done with question 1. Let's go to question 2. Question 2 is very simple. Very simple. So I'll go through this very quickly. Okay, so a point mass is moving on a plane. It means the x and y coordinates. Given that the position, so the x coordinate is given by this, y coordinate is given by this, where time is equal to this. Okay, sketch the path travel between 0 to 1, so 0 to 3 seconds. Okay, so first things first is we need to calculate the coordinates of the endpoints. Okay, the starting point is when t is equal to 0. The ending point is when t equals to 3. So let's do that. X equals to 1 plus 0 is equal to 1. X, and then, sorry, y equals to 9 minus 0 is equal to 9. So the first coordinate is 1, 9. Second coordinate is 1 plus 3 is equal to 4. Y is equal to 9 minus 3 squared is equal to 0. So the second coordinate is 4, 0. So this is the coordinate when t equals to 0. This is the coordinate at t equals to 3. Now we need to draw the path. Okay, draw the path. So x is given by this equation. Y is given by this equation. From the first equation, let's make t the subject. So t is equal to 1 minus x. Then we shall substitute this t into y. Okay, so y is equal to 9 minus 1 minus x squared. Let's expand this. A squared minus 2ab plus b squared. And then you simplify this, right? You should get minus x squared plus 2x plus 8. Okay, so this is a quadratic curve. So in a quadratic curve, you need to decide the shape, whether it's a concave up or concave down. Meaning, is it a smiley face or a sad face. So to do that, you check the coefficient of the x squared term. Check the coefficient of the x squared term. So this, is it positive or negative? If it is negative, then it's a sad face. If it's positive, then it's a happy face. So in this case, our shape is like this. Our general shape is a sad face. Then don't forget, for a quadratic curve, right, we have a peak. Okay, we need to find the coordinates of this peak. At this peak, right, dy dx is equal to 0. Let's go ahead and do that. So d dx of y is equal to 0 means we need to differentiate this with respect to 0. I mean, with respect to x. And then, okay, so then minus 2x plus 2 is equal to 0. Then x will become 1. Okay, so sub x equal to 1 into y. Okay, y equals to minus 1 squared plus 2 times 1 plus 8. Then this will give you 9. So you see, the peak occurs at the coordinate 1, 9, which just so happens to be the coordinate of the point at time equals to 0. See, 1, 9. Also 1, 9. So let me sketch out the path to you. The path to you, right, will be like this. So this is 1, 9. This is this. Sorry. Then it ends at 4, 0. Yeah. So this doesn't look very clear how is it a quadratic curve, but actually, right, this is actually half of a quadratic curve. So if it's a complete quadratic curve, it will look like that. But then since the starting point is exactly at the peak of the quadratic curve, you only see this. Okay, so this is the path that it takes. Okay, B asks for the velocity, right? Now they ask for the velocity at the point. So remember that velocity is the time derivative of displacement. First, we need the displacement function. The displacement function is given by this, okay? A column vector with x in the x entry and y in the y entry. Then they told us, right, the formula for x is this, formula for y is this. And now we want to find velocity, which is the time derivative of displacement. So you take the time derivative of this column vector. Okay, so now differentiate each entry with respect to time. Okay, so this is your velocity vector. But they want at time equals to 5, right? So at t equals to 5, v is equal to 2 times 5. And this is 1 minus 10. Or you can write this in ijk. So I minus 10j. Okay, doesn't matter. It doesn't matter whether you write it in column vector or ijk. Okay, lastly, what did they ask? If the point mass represents a body of constant mass 5 kg, find the total force. Okay, so we need Newton's second law. Newton's second law states that F is equal to ma. Okay, where a is the acceleration. Acceleration means the dv dt. Okay, dv dt. Now you need to differentiate the velocity with respect to time. So this is 5. And then you take your velocity vector that you derived, this one. So you need to do a time derivative of this. So the first entry will become 0. The second entry will just become minus 2. Right? And then you multiply it in. So 0 minus 10. Okay, you can write your force like this, or you can write it in ijk. If it's in ijk, it'll be minus 10 j. Yeah. So that's all the things for this tutorial. Yes, yes. Okay, yeah, that's all the things for this tutorial. See you next time.